all and welcome to this lecture. We are in module 11, lecture number 2. In this lecture, we will discuss about transit time and limitation of quasi-static model. We are going to discuss about transit time under DC condition, and we'll see what is the limitation of quasi-static model what we just derived for different reason of operation, that is strong inversion, weak inversion and depletion or accumulation. These are the learning outcomes of this lecture, which helps you to understand the concept of carrier transit time in MOSFETs and its significance as a measure of intrinsic device speed under DC operation. This lecture will tell you what is the basic limitation of quasi-static model what we derived so far by considering that voltage is varying very smoothly. This lecture will help you to understand the concept of charge pumping. Let's do a quick recap. In previous lecture, we said that in weak inversion, the inversion layer is much smaller than the depletion charge, and the depletion charge will not vary along with position, and hence the depletion charge can be simply calculated by multiplying W into L, whereas the inversion charge depends on X as Qi0 dash plus X divided by L into Qil dash minus Qi0 dash, and by putting in a simple integration we can get complete charge, that is W into 0 to L Qi dash into dx. So when you solve this, you will get ultimately what is the inversion charge in weak inversion. Then we solve for simplified all reason model, and we said that in simplified all reason model we need to change the variable from d psi s to dqi dash by just replacing d psi s by dqi dash by alpha into cox dash. By solving all these equations, at the end we have shown that how this charges varies with VGS. We said that when you change the VGS, the region of operation changes from accumulation to depletion to weak inversion to moderate inversion to strong inversion. First you will face the saturation, and then you will go for non-saturation because you are changing VGS, and you should take care of that limit of saturation and non-saturation boundary, which is defined by VGS minus VT divided by alpha. In this lecture, we will discuss about the transit time under DC condition. The transit time represents the average time required for an electron to travel to transverse the channel length, right? Meaning, if you have source here and drain here, the carrier will take some time to move from source to drain. That is what in general defined as transit time, which we have already defined in our earlier lectures, where tau can be defined as Q divided by IDS, where we are taking mod of Q and here IDS in different conditions, right? It is defined. The transit time provides a fundamental measure of intrinsic speed of this MOSFET, right? So let us consider different cases. In the first case, let us consider strong inversion, non-saturation case, right? It means in that scenario the inversion charge is given by this, which we have already derived in our previous lecture, where we showed that in strong inversion non-saturation case Qi can be given by W into L into cox dash into VGS minus VT, and we know that the current in non-saturation region can be given as W divided by L into mu into cox dash VGS minus VT into VDS minus alpha times of VDS square divided by 2. Let us consider that VDS is small enough, right, so that you can ignore this term, and hence if you just divide by Qi divide by ID, you will get what? Transit time. So I am rewriting this as W into L into cox dash VGS minus Vt, and in the numerator and in the denominator you will have W divided by L into mu into Cox dash Vgs minus Vt into Vds. This term get cancelled, this term get cancelled, and this will get cancelled. So ultimately you will get the transit time is equals to L square divided by mu into Vds. You see here that in strong inversion with very small Vds, the channel is approximately uniform, and hence the transit time depends upon L square times, right? And it also depends upon the Vds value. Let's see what is the transit time when you operate the MOSFET in strong inversion saturation region. So in strong inversion saturation region, the channel charge is given by this. Assume no velocity saturation, and hence you can rewrite the equation for strong inversion saturation as W divided by L mu into Cox dash into Vgs minus Vt whole square divided by 2 alpha. To calculate tau, again you need to do Qi divided by Ids. If you do so, W into Cox into 2 by 3 into L into Vgs minus Vt divided by W divided by L mu divided by 2 into Cox dash divided by 2 by alpha into Vgs minus Vt whole square. This term will get cancelled. So here Cox dash will get cancelled, then W will get cancelled, and ultimately you will get tau is equals to L square divided by 2 mu into Vgs minus Vt into alpha into 2 by 3. This 2 will go in numerator. So you can simply rewrite that as 4 by 3 into tau naught, where tau naught is given by alpha into L square divided by mu times Vgs minus Vt, where it is clear that in strong inversion saturation, without considering the velocity saturation, the transit time depends on overdrive voltage. Here Vgs minus Vt is called overdrive voltage. Let's see how we can calculate the transit time in weak inversion, considering Vds is just greater than 5 times of phi t. So in weak inversion, the charge is given by half of Wl into Qi dash, Qi0 dash, just we derived in previous lecture, and Ids also can be given as this. Because Vds is very small, that is what you can assume that Qi0 dash L goes to. Now by solving these two equations, you can get tau is equals to L square divided by mu into 2 phi t, right, which says that the transit time become independent of the terminal voltages, that is Vgs and Vds. So it is diffusion dominant, because in weak inversion the carrier will move from source to drain based on diffusion, and hence the terminal voltage is not coming in terms of transit time as well. So let's see how the behavior of this transit time can be analyzed in these three cases. If you are having Vgs is equals to 0 or very small, then you are in weak inversion. If it is in weak inversion, the moment of the channel charge is not dependent on the terminal voltages, and hence it will be related with the transit time given by L square divided by mu into phi t into 2. That is the maximum time. So in weak inversion, it will take maximum time to travel from source to drain, right? Now when you increase the voltage, then you are entering from weak inversion to saturation. So this is the saturation case. In saturation, you see your transit time is dependent on overdrive voltage, right? That is what this is the case, 4 by 3 alpha into L square divided by mu into Vgs minus Vt. So as Vgs is increasing, it means your overdrive voltage will increase, and hence the time taken by the carriers to move from source to drain in saturation region is decreases. Now this will go on decreases and follow, and this should follow this curve. However, there is another phenomena which we have already discussed, that is called velocity saturation. What happens in velocity saturation? If you have a channel and a source is entering to the channel at this edge, and suppose this carrier attained the maximum velocity, right? Then the time traveled by the carrier in this channel length is what? Tau is equals to L divided by Vd max. We have already seen that the Vd max now no longer influenced by the voltage. Whatever amount of voltage you increase at the drain side to pull this carrier, it already attained its maximum velocity. That is what the transit time of the carrier is decided by the velocity saturation limit and not by the terminal voltages. And hence, if you see in velocity saturation condition, the tau is given by, the transit time is given by L divided by Vd max, where this is the limit. So you are supposed to going this side, right? But because of velocity saturation phenomena, you are ended up with this. Interesting to see, the transit time everywhere depends on L square, right? In all the cases, if you see weak inversion, strong inversion, or strong inversion non-saturation, your transit time is dependent on L square. How can we physically relate this? Suppose your carrier is starting their journey at 0 and going to this point to L. It takes the time tau is equals to L by Vd, where Vd is a drift velocity. Now suppose if you increase the length by m times and decrease the velocity by m times. So ultimately the carrier would take L divided by Vd divided by m into m, will take m square time, right? That is what we are getting, the L square term. So the time will be more and it depends upon the channel length. Now let's see what is the limitation of quasi-static model, what we had derived so far for different reason of operations. To understand this limitation, let us consider a circuit where we are putting our MOSFET here and we are applying the terminal voltages, like this is Vg, this is Vd, this is Vb, and this is Vs. Considering here only we are changing the gate voltage and keeping all the voltages constant. To understanding what is the limitation of quasi-static model, we put the voltage VDD in such a way that transistor will be in saturation. Even when the maximum voltage of gate is attained, in the sense the transistor will not enter into non-saturation condition. Now compare the graphs and let's see what is the limitation we are actually getting when we are deriving a model in compared to experimental data. So this is the experimental data, the last graph, which shows that ID, when we measure, it shows that the ID will start after T2 and it will smoothly go to this point and ultimately reach its steady state. This graph is the graph obtained by our model, meaning here if you see the ID will be 0 till this T1 point, and after that it shows a negative value. After certain point, let's say at T2, it shows increase. Here there is a small hunch or there is a small spike and then this current get saturated. So this is the model result and this is the experimental result. So we need to compare these two results to find out what is the difference in modeling and actual experiment. Let's start from the applied voltage. What we are doing, we are changing the gate voltage very slowly. That is, we are taking a ramp function with some rise time of Tr. It is clear that the current will start after this Vt voltage, meaning when the gate voltage attain the threshold voltage, then only current start. Now you see, if I see the drain current here, that is the total current which is flowing under quasi-static operation. I can help you with this diagram, that we have drew this diagram as a fictitious MOSFET, showing that this is my inversion charge, right? Here drain terminal, source terminal, gate terminal, and here body terminal. So what happens is, the moment gate voltage increases beyond T1, the current starts, right? That is the total current. Again, this total current is modeled by a quasi-static model what we developed so far. Now at the same time, what happens is, we found the IDA, which is charging current at the drain side, shows a negative trend. Why so? It is obvious that when you are increasing gate voltage, the inversion charge in the channel should increase. How these charges will come? From where these charges will come? The charges will come from the source side. At that moment, the current at the drain side shows a negative trend, because the charges in going. So from where these charges will come from? These charges will come from the source side, and hence at the drain side the current will be negative, right? That is what we are getting, IDA is negative. Now when you use our quasi-static model, which shows that IDT is equals to IT plus IDA, and when you merge this graph plus this graph, you will get a small negative current till point T2. After point T2, the voltage is still increasing, and hence the current will increase and it will attain steady state value at this point. So this is major limitation of quasi-static model, which is not observed in experimental data. What is the reason behind that? You see, if a carrier is entering in the source, that is extra carrier, because of small change in Vg, the extra carrier is entering in the source, and this carrier will take some time, right? That's what we define as transit time. So the carrier will take some time to reach the drain. Until and unless this carrier will not reach the drain current will not start. That is what it is visible here. Until the point T2, the carrier is not reaching the drain. The moment the carrier reaches the drain, the current will start, and it goes as the gate voltage is increasing. Now the second limitation we have observed is, there is a hunch or there is a spike here. Why this spike is coming up? Because in our model we haven't discussed about the inertia of the charge, meaning when the charge entered here, it does have some inertia. It is not immediately go, right? It will not immediately settle down in the channel, and hence it shows some spike, which is not available in the experimental data. So we can again argue what is the problem with quasi-static model. The first thing is, we discussed about there is a negative current coming in, which we are modeling, which our model shows that negative current. However, the experimental data does not show that because of transit time issue. Now this negative current, which we are saying that's a charging current at the drain and source side, is dependent on how you distribute this charging current. Meaning, you can simply see that we define that the total charge or total change in charge in the channel can be defined as change in the fictitious charge at the drain side plus change in the fictitious charge at the source side will give you the total change in inversion charge, right? So in this change in charge, we can divide the contribution of this fictitious charge. If this is source side and this is drain side, we can say the ratio of these charges will be 50-50, right? Or we have seen in previous analysis where we derived the equations for QS in QD. When you operate the MOSFET in saturation region, then what happens is the ratio will not be 50-50. You remember there will be a term of 2/15 or -4/15 kind of term was coming. That is what the ratio is not 50-50. So the ratio can be 40-60, or in some sense we said that when you operate the MOSFET in strong inversion, then here there is a pinch off. Because of the pinch off, the ratio can be 0 and 100. So because of these two problems, right, what is the ratio you need to use? Ratio means what? The weighing factor which we have used in our calculation, whether this x by L or 1 minus x by L is correct or not. We are assuming, so assume that we are taking this ratio, that is 0 or 100, meaning the contribution of QD is 0 and the contribution of the QS is 100%. Then one problem is we can only define the charge is moving from source to drain, right, and not from drain to source. It is, we can only say that one dimensional direction or one directional flow is there, right. The another part with this is the advantage of this partitioning as 0 to 100 will definitely eliminate this negative current what we are getting, right. However, the problem with this is it will immediately start the current, which is this, and this is not a correct result, right. The correct result is the current should start after T2. So how we model it? That is what in a quasi-static approach we modeled by incorporating that there is a charging current which is negative, and because of that there is a negative transient coming into picture, right. So if you talk about the operations like digital operation, we are not much interested about the transition of the curve, whereas we are very much interested about what is the final and initial values. If let's say I am going to design a model for digital circuit application under quasi-static operation, then I will see what is the maximum value or the final value and what is the initial value, which we can say our model is predicting well. That is, this and this is approximately same, and this is approximately same. So this is a limitation which we need to take care of when you are modeling for quasi-static analysis. The another limitation we'll get is when the terminal voltage varies so fast, then what will happen? Then quasi-static analysis fails. And to maintain a system to a quasi-static, what we need to do? We need to divide the system in very tiny and small parts. Meaning, suppose if you have a source and drain like this, correct, and you are applying some gate voltage, this gate voltage is not changing slowly, it is changing rapidly, and hence the quasi-static analysis fails. To still develop the quasi-static analysis in this structure, what we'll do? We will split the structure in small sections, considering that each section follows the quasi-static rule, right. Obviously, when you connect these sections in series, then the source and the drain of each section will be different, and there will be a problem of charge pileup, right. So there will be a problem of charge accumulation that you need to consider when you convert this complete device into small section to apply the quasi-static model. There is another problem with quasi-static analysis or modeling is charge pumping. Now you consider a MOSFET that is N plus here, and this is the gate terminal. In general, the charge pumping is related to the falling part of the gate voltage. Let's consider that from VDD state you are decreasing the gate voltage. Now when you decrease the gate voltage, what will happen? The inversion charge which was earlier present, they needs to go out from the channel, right, and ultimately these charges will go out either from drain or from source. The removing of these charge from the channel through the source or drain is completely depend on the removing capacity of this source and drain, and hence the change in VGT, which is changing rapidly and showing the bottlenecks at the either end of the channel, results in some charges or electrons trapped. Again, in a layman word, suppose you have 2000 inversion charges present. Now, suddenly if you change the gate voltage like this, you are expecting that 2000 inversion charge will disappear. So these charges will go either from drain or from source, they will go out, right? But if the removing capacity of source and drain is limited, so let's say during that period 10 or 100 carriers left, right? So at this stage the voltage reaches to its negative value, so this become negative. You have some charges here, right, which is nothing but n, because these charges are what? Electron. So this is n type and your substrate is p type. So the local field induced junction, which is nothing but the charges, 100 charges you are which are trapped, and there is p type substrate, it becomes forward bias because the voltage is now negative and you do have some charges here, right? This become forward bias. Because the junction becomes forward bias, there is a current which will go this side, right? There will be a body current. That current is due to charge pumping, and this phenomena is called charge pumping. And hence, when you need to model for a quasi-static analysis, then you need to take care that the removal of this charge should also be there, right? Because when you change the charge, when you change the voltage with very small speed, then this change in the charge will also be small, and hence this will create a problem or limitation in our quasi-static model. Now let me summarize that in this lecture we have discussed about transit time of the charge carriers, which is the average time taken by the charge carriers to move from source to drain. The transit time provides a fundamental limit on the intrinsic speed of MOSFET. We have also discussed what are the possible limitations of quasi-static model we have derived so far. We have seen that in some cases the quasi-static model does not hold good because we have considered a very simple approximation, out of which one simple approximation was the fictitious charges Qd plus Qs is equals to Qi, and hence we considered that d by dt of Qd plus d by dt of Qs is equals to dqi by dt. This creates a problem to decide what is the weighing factor which we need to multiply to find out the total charge. We have also seen the concept of charge pumping, which is there and it depends upon the falling speed of the applied voltage. So we will stop here for today. Until then, take care.